Hi. So what we're going to talk about next is the four types of processes and how they look on what is called a PV diagram. And a PV diagram just is a graph that relates pressure and volume. So let's start first with the four definitions. And our first definition is they're not bad. Isobaric means that the pressure stays constant. As you might remember from your chemistry class or from some of the previous problems, we would say, given that the pressure is constant, what happens to the volume when the temperature changes? So that would be an isobaric process. The next is going to be an adiabatic process. That means that there is no heat flow. Now, from the last video, you might say, well, then there's no temperature change. Contraire. Sometimes the temperature will change and there's no heat flow. And we'll talk about how that happens and what that looks like in terms of pressure and volume. Okay. The next one is isothermal, which means there's no temperature change. So isobaric delta P equals 0, adiabatic Q equals 0, isothermal delta T equals 0. And if delta T equals 0, that means that there is no energy change in the system. And we'll talk about the implications and what that looks like in terms of the equations. And then the last one is isochoric, if you're old school like me, or some of the new generation call that isovolumetric. And that means that the volume stays constant. Those are simple definitions. And if there's no volume change, the volume doesn't change at all, that means that there's no work done. Add this up here. Okay. So what we have are just definitions. That's all it is. But these definitions will have very distinct outcomes and they have very specific implications. So what we are going to do is concentrate on these four processes. And we're going to draw what is called a PV diagram. So it's pressure versus volume. And we like PV diagrams because they give us a lot of information. As you recall, pressure times change of volume, and we're going to put a little negative sign in there, is equal to the work done. On the system. And that work done on the system gives us the negative. And we also know that from physics 1 that whenever I'm looking at a diagram, if I'm multiplying the two variables, my independent and my dependent variable, what I'm going to do is I'm going to find the area under the curve. So let's start with the easiest of the systems, and I'm going to make this a P final. Actually, just make that a P1 and a P2 and a volume 1 and a volume 2. And let's put these in SI units, pascals, and cubic meters, because we always have units on our diagrams, always. And so we're going to next draw our graph. So if I'm going to start at P1, V1, I'm going to start up here at point A, and I'm going to go from P1 to P2, and my volume stays the same. And I'm going to put a little arrow here. It says that I'm going in that direction, and I'm going from A to B. So the process from A to B, my volume stayed the same, my pressure changed. That is an isochoric. It's called an isochore process or isovolumetric. I will use isochoric. So that's an isochore, and that means that the work done is zero. Well, looking at how this goes, that should make some sense to you. I can't find the area under that because that's a vertical line. If you were looking for the slope, that's an infinite slope. So yeah, you can't find the area under that. So that is a really good indication that we're on the right track. So now we're going to go from B to C. So from B to C, what we see is that I've got some work done. And I went from a low volume to a high volume. So my final was greater than my initial. And this is what's called an isobar, an isobaric situation. And the work done is negative P delta V. And in this case, P2, because we were on P2 right here. And then V final minus V initial, well, that's going to be V2 minus V1. And V2 minus V1 is going to be greater than 0. So that's going to be a positive number. And that means that I expanded. Well, I can tell that I expanded because V2 is bigger than V1. My gas actually expanded. And so the energy left the system. Work was done. Work positive by the gas. And work negative on the gas. Which is the one that we will be using in this course. I like to bring those out because occasionally you will have a problem where it asks about by the gas. And you just have to pay close attention to what you're being asked to do. So this is my work done negative. So far, so good. So now we're going to go from C to D. And I'm going to go up here. And that's another isochore, obviously. The work is equal to 0 because delta V equals 0. I have a constant pressure. Okay, so next, we're going to go from D to A. Back to the beginning. And so that's a system. That's a cycle. And so I have cycled through. And funny thing here is that I've got P1. The work, let me have some consistency here. That is another isobaric line. And so we know that the work is P negative P delta V. In this case, my V final is less than my V initial. So work is going to be negative P2 times V1 minus V2. And that's negative. I get work positive done on the gas. I had to squish it. The gas compressed. Work was done on the gas. to make that happen. And energy entered the system. If you think about it in terms of mechanics, this is me pushing down on the piston. I put that energy in there. I added to the system. I had an external force, if that helps. So those are each individual situations. So what we're going to do now is we want the work done for the cycle. Work from A to A, B, C, D. Well, what you're going to do is you're going to add the work from A to B, plus the work from B to C, plus the work from C to D, plus the work from D to A. Well, A to B, 0, C to D, 0. And so now I just have to add those two. Well, one of them's negative, one of them's positive. Coolio. So now I've got the work A, B, C, D. The work from B to C, we just said, was equal to negative P2 times V2 minus V1. Plus D to A, come over here, that's negative P. Wait, one of those was P2. This should have been P1. Okay, that's my fault, not yours. Plus P1, negative P1, times V1 minus V2. Okay, a little bit better, a little bit happier now. All right, let's go ahead and distribute some negative signs here. Boom, 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 boom. And we've got W, A, B, C, D. So I've got negative P2, V2 plus P2, V1 minus P1, V1 plus P2, V2. Oh, that should be P1, V2. Sorry. I keep doing that, don't I? That's the second time today. All righty. Well, this is odd at best. So let's take my V1s together. My V1, P2 minus. So I've got P2 minus P1 times V1 plus P1 minus P2 V2, which it looks awfully similar to what I had before. It's just rearranged. That looks awfully complicated, doesn't it? But it isn't. It really isn't. All right, so P2 minus P1, that's negative. That's going to be a negative number overall. And this is P. Well, let's go over here and look at this. P1 minus P2 is right here. That's this side. V2 minus V1 is that side. What we're doing is we're finding the area of this box. Hey, wait a minute. Didn't I just say that I can find this P delta V, delta P delta P delta V is gonna be the area. Whenever we're looking at a diagram, if you're looking for the product of two axes, you're going to find an area under the curve. If you're looking at the quotient, like distance divided by time for velocity, you're finding the slope. Calculus peeps, this is the integral, the slope is the derivative. That's what we're doing. So I know that the work from A, B, C, D is the area of the box. Now, here's your trick. In this case, P1 is bigger than P2. So this is positive, right? V1 is less than V2. So my positive number is bigger than my negative number. My work is being done on the system. So if you are counterclockwise in my cycle, my work is positive. If I'm clockwise, my work is negative. Now, me, myself, and I'm not going to memorize that because that's a waste of my memorization space. And personally, I don't have a lot of that. But I can look at it and say, I had to compress at a higher pressure. So that work is positive. I expanded at a lower pressure. So I did more work going in than I did coming out. So work was done on the system, and that is positive. Okay, not too shabby. That is the nature of my PV diagram. In the next lesson, we're going to talk about doing problems with PV diagrams. We'll talk about an adiabatic, and we'll talk about an isotherm and what those look like. Okay? And then we will also discuss the implications from the first law of thermodynamics. Okay? Just remember, we're all in this together.